Okay, so and we are doing research in this area, trying to minimize the effect of geometrical variation in the final product. Some people are working very early, actually in what they call styling department in the automotive industry, so almost with the clay models. And then we go into more and more details, and some people are working in inspection data analysis in manufacturing, so on. So my story is really that as I said, I came from design. I did my PhD, finished in '95. I was inspired by Taguchi, Namsu. Then I went to work for a software company for a couple of years. So I became responsible for a software called Valis for variation simulation quite early these days. That was in '95. 3D CAD was not that old. So this was quite young type of software. We were using VSA inside. During that period, I got to know people at 3DCS also. So I got to know a lot of people in the VSA 3DCS organization. I also did a lot of training for Mazda in '97 when they bought a lot of Valis's VSA licenses. So I trained a lot of people there in Hiroshima. But during this period, I noticed that tolerance analysis was not very spread, or variation simulation, three-dimensional variation simulation was not very spread. They still used Excel sheets. Some in the US, Ford and GM, they did use it, but they use it very late. Often it was manufacturing people who did the simulations, or done by consultants sitting off-site, elaborating with the inputs until you get outputs that you could believe in. So it had nothing to do with reality. So since I came from design, I thought we must be able to do this much earlier. So then after a couple of years, I left that company and went back to Chalmers to start my group. I also started RD&T technology in that time. So I really felt that I had a mission to do this earlier. So we wanted something simple, to be used in early phases, and not so much functionality as all the other softwares. And now, after 20 years, we have more functionality than the other softwares. But that has been driven actually by the customers that we have. But also, what I found is in large companies, it's not so easy to, you have a number of roles. It's not so easy. You have more freedom in a small company. On the other hand, in a small company, there are other problems. You don't have money, but in a large company, the roles are divided. I will come back to that. So that was my introduction. In Winkvist Laboratory, we have 4 research groups: systems engineering, PLM, geometry, motion planning, automation, and my group, geometry assurance, robust design, minimizing the effect of geometrical variation in assembled products. And we are, at the moment, I have about 10, 11 PhD students. I have 5 senior people. I have something I came up with a couple of years ago. I have what I call industrial postdocs. It's my own PhD students that I have employed for 10% working with me still. They're in different companies, but we still do work together. And I also have some people at Fraunhofer Chalmers Center. And of course, we all know the reason why we are here. We have variation in the manufacturing process, in the assembly process. Gives us problems with assembly. We cannot get the parts together. We need to scrap or rework. That costs a lot of money, but it's an internal problem. Then we have function. If it's not discovered internally and it comes out to the customer, we can read about it in the papers, and there are quite huge costs related to that. And of course, in the automotive industry and other industries, but specifically in the automotive industry, aesthetics. Perceived quality is very much judged upon how good the split lines look. That's one thing, quite important. So you want your car to look well built. And to deal with variation, of course, we have tolerances, and tolerances is the key to mass production. Mass production means interchangeability among parts. So you need to define how much variation can we allow. And this started, of course, with mass production about 100 years ago. But really, there was some firearms with interchangeable flintlocks in 1778. But the situation is still, after 100 years of mass production, still the tighter the tolerances, the higher the cost. So that's why we need to think about robust design, of course. So in my group, we have developed a set of tools to handle this, to help minimizing the effect of geometrical variation. What we did in the early beginning was that we actually defined a very simple product realization loop. We say we have an early phase where we design the product and the production system or select production strategies. We have a pre-production. Here is typically where all the prototypes testing are taking place. And then we have production. Every company has their own gates, and in literature you have a number of different product realization processes. But we kept this one because it's simple. And so we work in early phases with robust design, variation simulation, joining simulation optimization, joining sequence optimization. We do inspection preparation, programming, offline programming of CMMs and scanners. We inspect, we analyze data, and we, of course, fix problems during production, but we also use the knowledge of the data in our simulations of the next product or the next platform. So this is basically how we work. Today I'm going to focus on this because that was the title, Robust, or Designing Locating Schemes. Designing Robust Locating Scheme was the title of the presentation, so I will stay there. So for us, it's really about two things. It's about the variation controlled by the tolerances, and it's about the robustness controlled by the locating schemes. And we all know that the locating scheme locks 6 degrees of freedom in space. We have now done a 2D example. In reality, we have three dimensions. And the best way I used to illustrate this is with a pointer. I have a pointer. I put the support in the middle. I say that this is input and this is output. So if I have the support in the middle and I put 1 millimeter variation in the input, I get 1 millimeter in the output. If I put the support here, I get more variation out. If I put it here, I get less. If I put it here, I get nothing. If I put it here, I get a lot. So this is neutral, this is sensitive, this is robust. And this is, as a designer, if you're in early phase, should reduce output variation. You could, of course, decide on tightening tolerances, reducing variation, or putting the support here. And if you do it early, before any tooling or anything, it doesn't have to cost anything. So, but this was one rotation. So you all know here that whether we like it or not, we have 6 degrees of freedom in space. When I put a part on top of another part, I lock the 6 degrees of freedom. I get contact in a number of points. So typically, I get plane contact, 3 points locking, 1 translation, 2 rotations, line or 2 points, 1 translation, 1 rotation, and 1.1 last translation. So if you want to have clarity as a designer, you design where those points are. Otherwise, you will not know if the contact will be here or here. So you cannot calculate. So this is the first thing, to decide where the contact points are. And I will come to that, but if you will use a software like RDNT, if you have an over-constrained system, if you have rigid analysis, you're not able to build a model. Because the first thing you need to do is to define the locators. So then you need to think, where are the contacts? So these locating schemes could be either the mating parts, part to part to part, or could be part in a fixture, or a number of parts in a fixture. And if you have variation in the mating parts, that will propagate to the part. So variation cannot propagate in the air. It propagates in the physical contacts, of course. So I will illustrate this with a demo, and it's always risky. So I sit down. I have to change between the PowerPoint and the software, and that's something that could Okay, so I have a car here. A car, a Volvo car. I want to do a tolerance analysis for some parts in the back of this car. So I will look at this rear lamp. I will look at the flush relation, variation in and out from the screen between the rear lamp and the window. I have defined statistical distributions for the different parts in the model. I can have any type of distribution, or I can have inspection data. I have defined locating schemes for the parts to lock the 6 degrees of freedom, and I have defined a critical dimension I want to analyze here. So in RDNT we do Monte Carlo simulation. So now I will run 1,000 iterations. I built 1,000 cars. Ready. So it takes no time at all. So if I look at the result now of this critical dimension, I have some limits defined, upper design limit, lower design limit. I can see I have a lot outside the red. We can see if we look at CP, CPK, 0.4, not good. I want maybe 1.33 or higher. If we look at 6 sigma as the measure of variation here in this demo, 6 standard deviations, 8.92 millimeters. That's not very good. We can see how that will look. So these are the maximum, minimum values of that result of the 1,000 iterations. So you like it? You want a car like that? No. So what do we do?
Change the locator?
Yes.
No. First, you make sure that you know exactly how much difference you can accept.
Yes. I have that already defined.
And you're sure it's the
Yeah.
Okay.
Yes, that's before this.
But actually, just one comment, that will not change the right position of the locator at all. Whatever demand you have, the perfect design wouldn't change.
But let's go back to this. Let's assume that we have put the ladder on the right wall. So okay. So instead of tightening tolerances, we will see, is this system robust? So what I do now is I may do what we call a stability analysis. So basically, I vary the locators, unit distribution, and I color code the result. I get a sensitivity matrix, what controls what, but we come back to that. But here I can see the sensitivity or the robustness. So blue is good, red is sensitive. So here it says 9.46 in the red area. So if I have 1 millimeter variation in the contact between the plastic pins inside the lamp and the sheet metal planes and the holes, I will get 9 times amplification here. Okay, so since you're all familiar with locating schemes, you will see that I have A1 here, A2 here, A3 here. They should be more spread out, of course. This is almost a line. So I've done this little extra here because of the effect. What do? We can optimize this, but we can also have a discussion where to put the locator. So now we have a discussion, and someone say, why not take this locator here, A3, and put it here? Somewhere. It's early phase. Did you see? So now the color coding is updated. So directly the color coding is updated, and we see now that we have a quite robust system. I can play with it more, but let's see how that affects the variation. So I put on the tolerances again and do the Monte Carlo simulation. 1,000 cars. Yeah, much better. I had almost 9 millimeters. Now I have 4.36. CP is better. It's not good, but it's better. So I can probably improve it a little more, and then I need to start tightening the tolerances. We can see how it looks. So, you know why I'm doing this? Because in early design stages, when we work with perceived quality, people don't know if the requirement should be 1, plus minus 1, plus minus 2. So that's why if we do it on a better projector, we use this realization, high-end visualization to give a hint of what requirement to put up. So actually, normally engineers don't work in this mode with all the glossary and everything, but this is actually a help to early phases because we don't know. Depends on how sensitive it is. Some areas people look at, some areas under the car, some areas is where the light falls. So that's why we actually do this.
When you say location points, you mean the assembly points?
Yeah. Okay. Since I think I stay here and sit here, I have another. Here we have something from. So this is typically the mode people working, the engineers. They don't have all the background and everything on. So here I have a part from aerospace company. In this case, we want to design a fixture to hold the part for machining or welding or anything. So somebody came up with this suggestion of a locating scheme. Let's see how good that is. See, red area is 50.6. So 50 times amplification. This means that if I'm holding the part in a fixture and the fixture has 0.1 millimeter variation, I will have 5 millimeter variation in the part where I'm supposed to machine. That will give me some problems. So now we can, if we want, we can optimize this. We can just tell the system what is the best position of the locators. Okay, get a new suggestion. Now we can see we have 1.83.
Sorry, but what does that comply to the function of the part?
I come back to that. So now we want to optimize the total robustness. I want to optimize the total robustness. So I want it. I want as many. I want to minimize the sensitivity in all the points on the part. That's a good start. So now I got this suggestion. Now we are not having an orthogonal 3-2-1. We have a 6-direction. We can have that. Probably we cannot put the locators here, but we can probably move them a little by hand and maybe come up with something that is close to it. So this is what's mathematically the optimal solution. I can show you that later, but you see here I have P-frame opt, I have pre-frame MEA, that's measure. So if I don't have a measure in this model, but I can select to optimize with respect to all points on the geometry or a specific or a couple of specific critical dimensions. So I have a slide on that. Since I'm here sitting down, we talked about axiomatic design. I was quite inspired of that in the 90s, and I thought I still am, but let me do the demo first. So here I will just use this to compare two concepts. So first, here I have a body, a door, two hinges. In the first concept, I'll put the hinges on the door to create a sub-assembly, and then I take the sub-assembly and assemble to the holes and the lock. So we do that. And then we do this analysis again. So now we see we have, if we look at the color coding, we see we have quite a lot of amplification up here. I will probably get problems meeting the requirements up here, whatever they are. If I want to look at if this is a coupled design or not, what we have done now, we see that output is the position of the part, input is the locating scheme of the part. So I vary the locators and I see what happened to all the parts. So if I vary one part and all the other parts move, then it's quite sensitive. If I vary one part and just that part moves, that is better. So and we sorted and tried to make it as triangular as possible, and the rest we mark in red. So this is a coupled design because a lot of parts are controlled by the other locating schemes. I can also, if I want, click on one of these, and I can see the sensitivity coefficient for each of the locators. So on an overall level, I see it's coupled. I can also see what to change. What is the most sensitive locator in what the most sensitive locating scheme? So we take another concept. We introduce a fixture. So in this concept, I put the fixture, the door to the fixture. I put the fixture to the body. I put the hinges on. So we do the same thing again. Now we see at least we have a fairly good situation here. The amplification of variation is lower. I get some problems with the hinges maybe. I don't know if it's important. I see that the matrix here, it's not totally diagonal, but nearly. So it's not so coupled. It's easier to handle.
Of course, because you took away the design skills and added a good center. Yeah. Why not design it? Right?
Yeah. But now we are in this stage of design. We have things earlier also, but this is what I'm presenting today. So we have worked with things. We work with styling department, perceived quality department, when you draw the first line and so on. But now we are in this stage. Of course, everything we do here could affect geometry. Maybe we could say that if I make the part bigger, I can put the locators more spread out. So in that way, it could change. So the last thing was actually a paper I wrote in '99 based on these things. The problem was actually that it's good for a demo like this. That's why I still like it. I still like the principle. I did it for the front of a Volvo truck, and we had a 40 times 40 matrix. So people ask me, what shall I do with the matrix? And I really couldn't answer. but I like the principles still. But two things we're working with large companies. It's not so easy to change the design because there's so many people. So if I manage to push it a little earlier than before, I'm happy. But I don't have the freedom I would like to. So that's why. Here is more the answer of your question. Here I want to weld this pipe to this cylinder. So I have a locating scheme for the pipe and the one for the cylinder. And when I do the first analysis, I do the analysis for the relation between. So I have a number of measures around here. So I do the analysis and I do color coding of that. Then I push the button, optimize, and I get this. So the locators move position to minimize variation here where I'm going to weld.
You're just doing the best fit.
Yes. No, but it's not inspection data. So it's not best fit because it's not inspection data. It's a sensitivity analysis to reduce sensitivity in this relation. I don't have any inspection data now. It's very early phases. I only work with rigid components, stability, amplification. So this is another type of part we are working with GKN actually to build fixtures, to welding fixtures. So this was all for rigid analysis. Now you have 6 degrees of freedom, and I think it's good to start with rigid analysis. But many of the companies we work with don't have any rigid parts. They have parts like this, when you have 14 locators in one direction, 7 in the other, and 1 in the last one. And if you have variation in the parts, variation in the clamps of the fixture, the part will bend. So it's over-constrained, you have bending, and you also get a lot of non-linearities because you get contact in points that you didn't know of. So then we have, in the software, we also have a finite element solver. which is quite fast. We started with importing, exporting, and so on, but then we embedded a solver. So we can actually handle over-constrained locating schemes, calculate forces, deformation, spring back. We have contact modeling. We can optimize joining sequence. Here we use generic algorithms to find the best sequence. We can handle stress. Or the sequence, actually, this is, I don't know if you can see it, but I have 2 parts in a fixture. I'm doing spot welding, 4 spot welds. Same part, same fixture, same cost, 2 different sequences. This is a good one, this is a bad one. Same cost. Stress, a lot of the parts that we work with, especially composites, you're not allowed to bend because, so we can do stress analysis due to geometrical variation. We can handle gravity. Large parts, they tend to be affected by gravity. We are also including composites and welding. So a lot of the things that we do, like welding, you cannot add variation from geometry to welding because they are related. So it's non-linear. You need to do it in every Monte Carlo iteration. So it's quite heavy. So, of course, we work with a lot of automotive companies, but as we heard earlier today, we are very happy that GKN decided to go from this concept with 1 part and no tolerance chains at all to this concept of welding together a number of small parts. So that will make us active for a couple of years. We are, of course... We live on this, you know. So we are, of course, designing fixtures, where to put the locators. We're doing tolerance analysis. And this is also the driver for including welding simulation into variation simulation. Because if you weld 2 parts together and you don't have a nice alignment, the melted zone will be different along the weld, and the shrinkage will be different. If you clamp them together, you will introduce stress, and you will have spring back. We work a lot, as I said, with composites. We're involved in a large EU project called LocoMax. I think most of the aerospace companies in Europe are involved. Here we want to build and verify wing boxes in composites. So it's a lot of parts, a lot of locators, assembly sequence, contact modeling, and stress and bending is not allowed. So, and they also do a lot of shimming. So they want to reduce shimming also. Building and construction. This is something I started to discuss with a couple of companies for over 10 years ago, where they wanted to go into more industrial buildings. So they want to make the parts in the factory, and then they want to assemble on site. This is something that they still think of. We've done some things, but it's going quite slow. But of course, you have the same situation here. I did some simulation. We come up with a concept for NCC, a large company in Sweden. So how to locate the walls. So we said that maybe it's good to live on the first 3 floors, and then after a while. So actually, I think we had this much variation between the walls on the 8th floor. So, but that's not my problem. I only designed the tool. Swedish company making furnitures. Actually, if you do rigid analysis, you can do this type of analysis. So you need to say, okay, I fix it here, here, and here, and I measure the distance here, the gap here, and then I say, is it possible, do I think it's possible to get it together? But I cannot assemble it if I only have 6 degrees of freedom. So if you do non-rigid analysis, you can just put them together and allow a little bending. And then you can, of course, check the stress level, is it okay or not? So that company had a lot of tolerance problems, but before we had non-rigid analysis, I didn't want to approach them because I knew that everything was over-constrained. And so dental applications, not so nice pictures here. They do a lot of experiments on pigs. So the users of RDNT are mainly automotive industry, of course Sweden, but also Jaguar Land Rover, Pininfarina, Ford, Renault Trucks, a lot of suppliers and consultants. But it's also growing. I think automotive industry is a little special because they are under so much pressure, so they don't have any time for physical prototypes, testing. They need to rely on virtual models or simulations more and more. So that's special. Also to our development process, the loop we had a number of documents. So we're starting early in styling, defining requirements, and then so there's a set of documents where you document all the things you do. So there's a working process together with this. So, thank you.
Yeah, thank you very much.
Oh, it's you again.
A couple of others come back to you.
Yes, I asked some of the technical universities in Denmark about can they simulate welding deformation in 2D? Can you do that?
Yeah.
Okay.
We can do it. Yeah, we can do it. But I mean, there are commercial software for this. There are a number of them to do this in 3D. What we are doing is we are embedding the algorithms in our software to get faster calculations. But we can do that. There are a number of different theories. The problem is it takes time. So we have a full simulation with all the transients, everything. But we also have some faster to be able to do it together with Monte Carlo simulation, or at least a number of different samples. So, yes?
What did we say, Thomas, when you contacted us?
It was the Force Institute. They say they couldn't
Okay.
simulate the 3D.
No.
We should get
I mean, not everybody can. We have some institutes in Sweden that are experts in welding and welding simulation, but it's a tricky area. I've been working with Professor Goldak in Ottawa. He's the one behind all this welding simulation and defining the melted zone and so on. So we had actually the first things we did was to integrate his software with our software. But now we know how he's doing it, so now we are doing it directly. And he's also getting old, so we need to. We cannot rely on him.
Any other questions? Not yet.
I have one.
I kind of got the impression that you feel that axiomatic design kind of has its limits. You mentioned that you defined that a system was coupled, that you couldn't solve it.
Oh, we can solve it, but it just. If you are presented with the fact that this is a very coupled system, and you're not in the power of changing it, so I mean, but if I still think it's very good, I did actually I had no demo of it, but I did a job for Husqvarna in Sweden. They had one small engine, which was their own, and they say, okay, when everything is working, it's a very good concept, but don't touch anything. And then they wanted to create a platform. So they wanted a concept that they could build similar variants on. And then they were looking at the competitors. So I analyzed the two concepts. And I could show them with this type of matrices that their concept was very coupled. So if you don't, when it's working, it was good, but it was very sensitive. And the competitor concept were not. So they went for this one. So if you can convince people that reducing the number of input parameters is a good strategy, then I think it's a very good tool.
Do you have a way of kind of synthesizing the way to uncouple it, or do you have to start from scratch when you hit that problem?
Normally, my answer to this question is that, of course, we have some sensitivity analysis and so to see what is the most influencing parameter, and then you can see, could you do something with that, change that part, change that locator, move it, or something like that. Otherwise, in many cases, in automotive industry at least, they say, okay, we have three concepts. Which concept is the one with less risk? So we want to minimize risk in the concept we select, and then we can. So then we check all the concepts, and we can see who's the best one, which is the best one.
Okay, we've got 2 more questions here, but we're not going to have time for the discussion session, so I suggest we carry on with questions, but we can also direct questions to other people in the audience, or have a bit of a discussion back and forth for the next 10 minutes, and then I'll go into closing. But until then, we have Janus and Lars. Janus, go on.
Actually, looking at these, how can I say, component-to-component location scheme 6 stuff, like you were talking, like I was talking about as well, is that how much do you actually work in mechanism system with all these elements or locating schemes?
Actually, not so much.
No.
Since we are, I won't say that we are driven by our software, but a lot of people use TI-TOL, CE-TOL when it comes to this type of mechanism, which is not Monte Carlo simulation based, where you create a relation. But we could do. I mean, we can describe all the joints, everything like that. And actually, we have done, like for moving doors, boot lids, things like that. But then we just have a number of positions.
It just strikes me when I see this simulation that if we combine that type of simulation with the study of mechanisms on a total car.
Yeah.
Because normally a lot of the noise factors is actually coming from the overall system. That means that even though we have perfect component-to-component interfaces, the system is acting as one, I'm going to say, combination of location schemes.
Yeah.
And these location schemes has exactly the same ratios that you're talking about, just on a higher level. Meaning that the whole embodiment, or what we call it, of the system is actually doing exactly what this simulation, just on a mechanism level.
Yeah, we have done it for robots.
Yeah.
So if you want to see that the robot has a certain precision anywhere in space, you have the problem that the sensitivity coefficients change. If the robot is like this or this or this, you have different sensitivity. Yeah. So then we have done optimization things to optimize what tolerances to put on all the parts with respect to all the sensitivities to be able to keep ±1 everywhere in the room.
Sorry, just one more comment. Because what I really think is the beauty about the locating scheme is that now suddenly we are coming into what we are doing about it, the design. And looking at the motor and this from Rolls-Royce and this type of very complex, we could actually look at it as mechanism systems moving. And when we start doing that, instead of looking at it as structural finite element analysis of what we have in random done, we suddenly are very, very close to what to do about it, because it's just about moving flexibility and moving rigidity to the right component, to the right location scheme to minimize the ratios. And that is robust design. So I'm very inspired on that.
Take that as a comment then.
Yeah.
It's just that it seems like all these locating points, I mean, when I do GPS on items, I keep asking for the functionality and the interfaces, and I use those surfaces to make the datum systems that create the assembly.
Yes.
Which is what I call functional GPS, basically, not just unconsciousless GPS. But what you do with all your contact points is that you move the assembly points to the contact points, am I right? So you steer or you control the assembly by fixing points in the toolings and the fixings.
Actually, this is something that is quite confusing outside the automotive industry, but you should have what they call the master location system. You should have the same points when you manufacture, when you inspect the part, and when you assemble. This must be the same, because otherwise you change coordinate systems and you have variation. You cannot make coordinate transformation because
so you take away
same points. That's number one.
You take away the natural assembly, but you made a specific assembly guided by specific attachment points.
That they have normally. Yeah, sure.
Yeah, so this is the fixture. Either the mating part is the fixture or you put it in the fixture. But you need to decide where those parts, where those points are.
Sure.
With respect to overall sensitivity or critical areas.
I have a question also. It's an incredibly good bit of software, partly because of the visualization aspects. Your input variation in RD&T is geometric. millimeters, angles, and so on, and your output variation is also geometric, millimeters and angles. I'm just wondering, can it be adopted to other outputs?
Oh yes,
Forces,
we have stress, as I said, but we also have interfaces to like Adams for handling simulation. So we look at the subframe of a car and see, because that was not symmetrically put together, so that affected handling behavior. We could look at flush between doors, export this result to wind noise simulations and so on. So of course, when geometry is one of the critical things, but there could be others also, then we are input to this.
Well, I really like that, because there are these other software approaches, but on the input side, on the input geometric variation side, they don't have the visualization aspect that RD&T does. So if you combine that with these add-ons to the other domains and disciplines, I think you definitely have something very powerful.